Hello, everybody. So, okay. So I will speak today about machine learning for short-term demand forecasting on the Quebec power grid. So this is a common talk with Arnaud Zinflou and me from Hydro-Quebec. But of course, in fact, this is not a talk of two persons. This is a talk of many persons of Hydro-Quebec and many students from Quebec and some from engineer schools. Oh, is there any? Okay. Okay. So I will briefly describe Hydro-Quebec and some motivation of short-term load forecasting. And I will briefly introduce energy transition and climate change challenge for load forecasting. And briefly, I will speak about open source and open data in this project. And I will introduce the short-term load forecasting Python library that has been developed by Hydro-Quebec for 6 years. And I will describe first use of this lib in operational conditions. I will try to underline the strategy we adopt to reduce the R&D time to market. And I will propose a first post-mortem of the use of the deep learning in our system. And I will show you some real-time results by using the operator screen at the same, just after. And I will speak about briefly about bottom-up forecasting, and I will conclude on some perspectives. So Hydro-Quebec is the largest power utility in Canada. This is a world leader in hydropower and large transmission systems. I propose to hear a short movie of 2 minutes. And sorry for the music. Okay. I hope that it will work. Okay, I think that this is the end of the movie. The benefit is at the end. Sorry. So this is the research center of Hydro-Quebec. This is, I think that this is only one utility in North America with its own research center. And I think that it is really important. Okay. So, thank you. Okay. So load forecasting is crucial for electrical power system operation, for transmission management, generation management, sales planning, and distribution management in the town and community. And what is difficult in Quebec and what makes really interesting our project from a scientific point of view is that the load is there is a great impact of meteo on the road. For example, you see a typical daily load for in winter that you can compare to the daily load in summer. It's completely different. And we have very important ramp up here, here. And we'll show you what happens with our historical peak 1 year ago. And our load is highly sensitive to the meteo variables. For example, with a variation of plus or minus 1 degree in Montreal, we will have a variation of minus or plus 600 megawatt. And for a variation of plus or minus 5 kilometers per hour for the wind, we have a variation of plus or minus 200 megawatt. And same thing for the cloud with a lot of or very few cloud. We have minus 600 megawatt to 300 megawatt. And it depends of the type of cloud, in fact. And here you have what we call the banana curve in our company. In fact, we have here the temperature minus 30 here and plus 30 degree, and here we have the power in Quebec on our electrical grid. So you see that we increase the power when the temperature decreases in winter, and we have the reverse in summer. So this is due to heating here, and this is due to air conditioning here. So we have in fact 3 regimes. We have the winter regime, we have the summer regime, and we have something which is difficult, which is the transition between these 2 regimes. We can compare this to in fluid mechanics to the transition between laminar and turbulence, with which is difficult to manage. So in fact, we have to be able with our model to manage all this behavior with this transition here. So if we see the consumption of one consumer, we see that the shape of the load is similar to the load for the Quebec. If we see the consumption of one commercial business, we see that we have something which is different. We have something which is quite constant in the day and which is very low in the night. And if we, in fact, for heavy industry, we may have something which is constant, quite constant, 24 hours a day. And the energy transition has an impact and bring new challenges for the load forecasting, because there is behind the meter production, renewable production, electrical vehicle. We have a smart grid, smart meter, and we have mutation in the heavy industry, for example, data centers. And we have new social behavior with teleworking. So all these phenomena will impact the load forecasting. Here you have a movie with the real load, and here we have the forecast, which is more accurate in the day. Sorry for my English. So here, this is the climate change impact. So it's very clear that we have more and more extreme events. The first thing is that we have an average increase of the average temperature. Okay, so we have a translation towards the up of the banana, but we have two things which are very new. This is the extreme events. So in fact, there is a deformation of the banana with more points here and more point here. So how will be the banana in 20 years? A boomerang or a cycle, a donut? I hope that it will remain something like this, but we have new events, and I will show you one event and how our legacy models, the behavior of our legacy model with these extreme events. Okay, so with climate change, there is a change in the world, and which affects also Quebec, of course, with renewable electricity generation, so a linear increase and an exponential increase here. And with the car, this is the same thing. And we think that it could increase more in the next year to be carbon free. So all this change the behavior of the electrical system, and so we have a new challenge. So open source and open data. The energy transition does not end, of course, at country borders, so we have to make common efforts to face the upcoming challenge. So open source at Hydro-Quebec are already used with classical library or tools, TensorFlow, PyTorch, Linux, and so on. And Hydro-Quebec is already involved in the open source community. Hydro-Quebec has joined the CRESIM and, of course, the Linux Foundation Energy Consortium. And we have this year published, if you are interested in, a paper in the Journal of Open Source Software for a new Julia package which solves a constraint nonlinear least squares problem. So if you want to upload it to test it, it will be good for us. So Hydro-Quebec has opened our data. Most of these data are also in French or only in French. So we have electricity demand in Quebec, in live, and we have many others important information which describe the behavior of our system. So the Hydro-Quebec short-term load forecasting lab. So how did short-term load forecasting lab come about? The first initial commit was in 2019, and we have a first merge with a bottom-up and top-down approach here in 21. And we have a new commit here, and we are here now. So I will describe the use of this version. And we have this version here was used in the energy transaction floor. It is more simple to use this library here because the security constraint is very low compared to the security constraints that I will describe to you after. It explains why we have delay, but we can use the information, a retour d'expérience, expérience, je sais pas comment on dit, of this team. So this library has many models. Among them, there is a deep learning model. And I will focus for the top-down approach on the TCN model, temporal convolutional networks. And we aim to use transformer networks in next year in our operational area. This type of network comes from generative AI, and this is already used in the transaction floor parquet in the energy transaction flow. We can, with this library, we can produce deterministic forecast, and we can also produce probabilistic forecast with quantile. And to define our model, we use a JSON config file. I will show you after. Here, for example, we try to use the TFT model. And we define hyperparameters model here. And we define the type of prediction we want to do top-down, but we can put bottom-up or PSAT for satellite substation, if you want. In fact, when we produce two different models with our library, we have to choose which is the better of this model. And so we have many measures to select a model. So if we use this measure, perhaps this model will be the better for this model. And if we use a second measure, this model will be better. In fact, this measure depends on the choice of the operational team. If the operational team focus on this type of events, perhaps he will want to use this measure because this model is not so good compared to this model for these events. And this is and another team, for example, the transaction floor parquet, want to focus on other part of the curve, and this measure could be better. So with we don't know exactly which is the best measure, and that is information that we will learn, which depend on the reality of the operational team. So how can we find the best hyperparameter? The second thing is that when I show you here that to define the neural network, we have to choose a hyperparameter which defines the structure at a high level of the deep neural networks. In fact, we can plug, here we impose the values, but we can plug an hyperparameter optimization. For the moment, we have we use this type of hyperparameters optimizer, but we test at the research center 3 other hyperparameter optimizers. So we will be able to use different optimizers. So, for example, for the last one model, with the hyper-optimization with random search, we for this measure, we have a best model, but of course, the CPU time is more important because we plug an hyper-optimization. So top-down forecasting and a first use of the short-time lab in operational condition. So I will try to describe the strategy that we use to reduce the R&D time to market with the CASTOR lab. And I will show you first result and first post-mortem. I will show you in live the behavior of our deep learning model with the results. And now, we will see now. So I don't know how will be the results, all the results. So a brief history, the Hydro-Quebec legacy models has been developed during 30 years by former Hydro-Quebec engineers. So this is a parametric model. It uses Fortran language. So the number of line of code is very important. The number of parameters is about this number, and some parameter has to be fit by hand in a very difficult situation. I will show you 2 situations. And it's very difficult to maintain, and we need to rethink. And what we see is that since this day, we have a degradation of the model. And it comes from the fact that before the network was stable. And so the modeling was good. I compare with in fluid mechanics, if you want to define a new plane, and if the Navier-Stokes equation change in real time, Boeing and Airbus will have problem because they will have to redefine the model. So this is the same thing. We want to model the reality, and this reality change. So this is very difficult, and the velocity increase, in fact, and the complexity of the network increase. So it's difficult to rethink all the modeling. For example, this function model exactly is supposed to model exactly the heating. And, but this is the heating 10 years ago. How will be the heating in 20 years, for example? So it is simple to define a toy model to explain that mathematically that we will have problem if we stay with this technology. So we have, for example, for the historic peak in Quebec, so the 3rd February, 1 year ago, this was a polar cold with a felt temperature of -40 during 4 days. So it was very, very difficult. And what we see is that Thursday, the curve is normal. And when we enter in the polar cold, here, about in the afternoon here, we see that two things. The first one is that we was with a high sub forecast of the power. So we had to inject many power. The second thing is that there is no afternoon hollow delay. You see that a typical profile in winter, there is a hollow here and here. So try to think to be an operator in Hydro-Quebec, which work in real time. It does not know what will happen here. It's here. And you see, it increase. But my habit is that there will be a hollow. So, do we have lost is the information okay? Do we have lost the control of the system? It's very extreme situation. The second thing is that during 30 minutes here, we have increase of 3,040 megawatt per hour. If we relatively to the French population, it will be, we have to open 50% of the French nuclear fleet in 30 minutes. So it was very enormous. So Manuel, so for the load forecasting team, we had to inject 2,000 megawatt to correct and to delete the hollow, to take the control of the system. So that's what you see. This is the movie of this day. You see that everything is okay, and at about 1:11, everything. This is the first load, and after you see that, and okay. And what you see is that we inject correction here with this. So this is equivalent to 2 nuclear reactors here when you inject this power. So AI first attempt. We have a first prototype in 2018 here. And what is interesting to see from a scientific point of view is that you see that the model firstly capped the large scale, the large time scale, and after the tiny scale. And this is classical in deep learning. And another thing is that with this type of model, and with deep learning in general, we can construct many models, and we can aggregate all these models with another optimizer to obtain another model whose performance is better than this 5 model. And we see that the frequency of tiny error increase for the aggregated model, and the frequency of high error decrease and goes to here. And the strategy to go to deep learning from this prototype was to construct a university computed lab in our operational team, which is open to the outside world, making optimum use of the power of cloud computing. So now we have in this lab here, we have firstly the load forecasting team, but now we have also the wind energy forecasting team, the meteo forecasting team, and IT team, and some people of this team, and HQ Research Center team, and Canadian University, and some student from French has also used this lab by using a protocol. In fact, the COVID-19 has accelerated this because we wanted to work with these students who couldn't come in Canada. So we have built a security protocol to allow them to connect to a virtual machine in HQ with their laptop, and from this machine to connect to our lab. Here, only the forecasting team can reach this secure area with two levels, a dev level and a pre-prod and prod level here. And voilà. What is important to note is that the load forecasting team is architect and administrator of this cloud lab. So this cloud lab is, and secondly, this cloud lab is free of high-level services of the cloud provider. Here, this is AWS. So this is excellent for easy portability of our AI ecosystem plus low cost. So it explains that we have developed all our AI tools here, or validated our AI tool developed at the research center, and it was plugged automatically in this area without any bug in 6 years. So if I zoom on this lab, we have, like in a classical university lab, we have a server here, and each server has a function for the development, for high performance computing with GPU or CPU, with the high performance graphical treatment for massive data, and to test new solution with no SQL language, and to test MongoDB, to test without any risk solution, and for other projects. And here we have cloned the security, the area, which allows, so these three machines are exactly the same as this three machines from the hardware and software point of view. This allows to develop, when we develop something here where we have no constraint, we will test our model here, and the student or researcher can test their R&D in our constraint situation. So this accelerates and the R&D time to market. Okay. So the cycle of our R&D is the following. So in the first step, we develop and validate our AI tools in our CASTOR lab. So the two teams are involved in this step. In the second step, we will train the new models that we have developed here. For example, the TCN models. In the third step, we will launch many real-time experiments. I will show you also that during weeks and months by the operational teams. So in this area. And after, we will upgrade, we will select We will verify the conformity, that there is no bug, many things. And we will test also the accuracy of the new models, and in teams, the teams will choose which model to pass to the pre-prod and to the prod. And after that, they will retrain TCN models in the lab, and they will do this step. And after, when we have some experience of these new models, we will do post-mortem of the R&D with the real-time and actual operational tools. We will do new R&D steps to correct some issues and to improve AI. And there is a constant communication between operational tools, team, and researchers, as you see. In each step, the operational team is present. So this is a continuous cycle. R&D is developed in parallel with operational postmortem. This is easy to test, accept new technologies for everybody. So this is the change management. It's very important. There is transparency of our results. I will show you also that. Everybody is confident with what is delivered. We see that there is an exponential increasing of the curve learn. There is a reduction of the R&D time to market and a reduction and control of the cost and of the risk of the R&D. So during these years, we have prepared the tools with perceptron, multi-layer perceptron, knowing that in 23 we wanted to use deep neural networks with temporal convolutional networks. So if I had in the history of the commit, we see that here that we have the first AI model in prod, multi-layer perceptron model, but we didn't use it to forecast the official load in Hydro-Quebec. This was to prepare the infrastructure with deep neural networks. And here, so it took 2 years here. And after here, the commit here with TCN, we took 1 year to upgrade continuously the tools and to be prepared for the first launch in this date. And I will show you also results where we propose really the official forecasting with deep neural networks in Hydro-Quebec. So I resume our situation in this. We have the legacy models here, which was developed during these years. We don't have the right to stop the service, and we have to pass to this technology here. And prohibition on stopping service, conservatism, fears of system failure, obligation to bridge a gap between old and new system, obligation to run several technologies, so for example, Fortran and Julia and Python. So the risk of stress for everybody, and need to be organized, planned, realistic, and transparency with the patient. And the next step, this will be the bottom-up. So results, in October 23, 1 year ago, at this hour, there were the first calculus with the TCN deep neural networks officially. So we see at this day, we see no bug, and the curve was quite similar to the legacy model. So here, this is the real load at 10 in the morning. Here, this is the first legacy model, the second legacy model, and the deep neural networks model, which is the blue curve here. And at the end of the day, everything was OK. And we chose this day because the meteor was quite good. And this is like a rocket launch, in fact. So we wanted to take a day where the meteor was controlled and OK. And if we see the results some months after, for example, this year in May, we see that our deep neural network model was very good on this Sunday. This was Sunday, and this was Monday, holiday day, and this is very difficult. This is more difficult to forecast the load on holiday. And sometimes we have to put some correction in the legacy models to be able to manage this type of days. And what you see here is that the deep neural network was very good without any modification. So another extreme event, this was this year with a felt temperature of 39 in Montreal. And again, there were dilation of the afternoon hollow here. You see here. And this model was unable, again, to cap the fact that there were no hollow. And so we have to put many correct power here to control the situation with the legacy model. But what you see with the deep neural network was that it forecast the afternoon hollow dilation in this situation. So there were errors here because this was very atypical and extreme for this temperature. So what you see is that this is the same situation as the polar day, but with heating, with air conditioning compared to heating. And another important point is that from April 4th to August 12th, we have 46 retraining of the two legacy models, parameter optimization. And here, with this TCN model, we had only 2 retraining for this model, so reduction in human intervention by 95%. So bottom up, okay, I will show you before bottom up. I will show you here. So here, this is the reality in Quebec up to now. I will do actualize. So you see that our TCN model here is very good here this day. And if I look, I will show you what happens here during 1 week. So you see here that the TCN model was very good. So this is the blue. The older legacy model is the yellow, and the most modern legacy model is the red. So here, 31 August. Okay, I have to click 2 times. I don't know why. So here's the hollow. 1st September. Okay, we have here the deep neural network has difficulties compared to this, but in fact, if we have a look on the 1st September, we can see perhaps that the operational team has put correction. So I will show what happens on the 1st. So no correction of this day. I discover the results with you. So here, the legacy model was better than the TCN. So 2 times, okay. So here, it was better, and after between the two. And what you have to understand is that this TCN model is I don't know how to say in English. Is restricted because we want to upgrade the deep neural network gradually to see scientifically the improvement, and that our team take the knowledge of all the parameters. So this is for human reasons and for technical and scientific reasons. So this is third. I have to type 2 times here. And I come back to 6 here. And you see, I speak about some experience. So all the team are involved. So this is the dev area in the secure area. So what you see is that each, so this is the step 3. Each person of the team here has launched its own experience. So each experience has a name: Apollo, Iris, Illimani, Sajama, Tarzan, Pollux, etc. Each experience is one TCN model. So each member of the operational team can launch this experience. They train the models, they choose by team the experience, and they design this experience. And after, we have what I call the meta rapport here. So this is the transparency, which is sent to 50 persons and our directors, where we see the results for each experience for 1 week. So you see, for example, Apollo, he has these results, and Pollux, etc. And we let all the model, so this is a perceptron model, for example, to see how it is, comment il vieillit, how, I don't know to say it. How he aging, yes. Okay, thank you. So I will come back to the bottom up and to conclude. So the bottom up, so what we have to understand is that the bottom up use the same library. What is different is the data are different. Of course, this is massive data here. So we have to monitor many calculus. So the infrastructure is different. And the output, we have to manage very big data. So this is different. So the bottom-up approach is based on the advanced metering infrastructure data, which come from 4 million customers. So we have some tools to automatically correct, for example, the data. So we cluster the data with different models here, and with different profile of consumers. And we were able to scale to large data set by training several hundred of models in parallel. So in pre-prod, we have this number of models, and in dev experiments, we succeed to train in parallel 1.5 million with the same library. This is important to understand. Remember that we commit the top-down and bottom-up some years ago. So we introduced generative AI. This generative AI is already used in the transaction flow, and we aim to use this type of AI in next year. So there is, and we will use transformers, in fact. Transformer there is a huge amount of models. That's why we have to be organized, because it's horrible. So organization is the key point of the R&D, in fact. Okay, so I don't have the time. So transformer is is much more complicated than, of course, perceptron and than TCN. So see, I don't have the time. This is for temporal fusion transformer. I don't have the time. So recent change in society and the impact of the energy transition are current and incoming challenge that implies the development of new and more flexible tools and algorithms. These tools should be more automatic and able to capture local properties, top-down AI-based approach was successfully deployed in production at Hydro-Quebec with competitive results that improve overall forecasting accuracy. Bottom-up methods are a way to exploit the data of smart meters, and diversity exploiting multi-scale structure is a key for results aggregation. And the future war is to incorporate new variables, new weather data, a continuous improvement with the operational team with the top-down approach, work with industrial and academic partners, extend the use of the library to renewable energy forecasting, solar and wind, go further with work on smart meter data, and etc. And I will conclude with this. In fact, we need also to inject dollars in the AI long-term research, in my opinion, even if we focus on the development of applied open source tools by reducing the R&D time to market. Because there is many theoretical mathematical questions that are opened. And in my opinion, there is a parallel between kinetic theory of gases and AI with smart meter data to do. Because we want, perhaps, we could be able to define a power density instead of a density at a Dirac point, at discrete point. This could give a power continuum by geographical area. So we will have microscopic models, mesoscopic models, macroscopic models. So several change of scale, like in fluid mechanics, with atom to continuous material. And it could be theoretical tools to meet the future challenge of managing large volumes of data. So I conclude with, again, acknowledgement with all these people, and thank you. Yes, sorry for the question. Yes?
Yes, if I understand correctly, none of your models are open source?
It's not still open source, but we want to make open source at a time. This yes, yes.
Would you consider partnering with OpenStaff to potentially adopt that model, or would there be a reason to not do that?
We are open to everything, in fact.
Okay, so you might.
Like my director said, the two constraints is I want to earn money and I want to control the system. So. Yes.
So I'm curious about your. I've been doing a lot of the load forecasting work for the NERC load modeling work group, and we run into a lot of troubles with evaluating the performance of these models because typically you have to select your holdout data set, and which holdout events you choose have an enormous impact on how you evaluate the performance.
Okay.
And what we found is that if we hold out, for example, peak events, we measure one kind of performance, how well does it do predicting the peak, versus if we hold out the high ramp events, you get a completely different performance evaluation, and you end up actually tuning the model to sort of different conditions, and it's not always obvious which one you should be doing holdout or whether you should just do random holdout, in which case you typically start to focus on predicting sort of everyday normal behavior, which is not really what we're interested in, we're concerned with. I'm just wondering whether you've decided how to do the holdout, or whether you do different holdouts.
In fact, this is a continuous increasing. So we have to learn at the same time we put in pre-prod or prod. So this is a continuous cycle. So I don't have all the answer to your question, but this is questions that are clear. For example, that's why which one to choose. We have two models, which one is the better, and it depends on the type of measure I choose. And this type of measure could focus on the peak or on the ramp up. That's why this model for this measure, this model is better than this one. And for this measure, this model is better than this one. And in fact, this is the operational team which will choose with their reality which is the better measure. The second thing is that we also study dynamical ponderation of model with optimization, with constraint, which could depend on this type of choice. So we have 10 models, and automatically, there is a model here, for example, with perceptron here. Ah non, c'est pas là. OK. Perceptron, c'est où? OK, on va y arriver, c'est ça. So, for example, there is 5 model here, and we could choose this model is perhaps more designed for the ramp up, and this one is more designed for the peak. And we have we develop dynamical ponderation to automatically goes to this one. So this is classical optimization. Exactly. But at the present time, in the operational monitors, that screens that I show you, the ponderation is constant. But we have all what we will be able to have dynamic ponderation. It could be very interesting for cyber attack, for example. And so we could have one model which is very robust with ponderation equal to 0, and attack, there is no information, and so this model has no data, what happens, so automatically 0 for this and 1 for this one. So we can do many things, in fact. Okay.
Is it possible to segment scenarios where legacy model comes out to be better than the new ones, and in that case, is there any optimization using the legacy models, for example, or a mix?
Yes. In fact, we can mix the old technology, which has difficulties, but in some situation it remains very good, even better. And so we don't want as now to garbage our. So this is a continuous, but we can of course ponderate. This is what we do actually. For when we have a look on the real situation here, I will show you the ponderation here. So here, this is the real situation. There is 3 models, and if I have a look on, so this is no correction. If I go to see the ponderation, in fact, you will see that the team is not still perfectly confident with the deep neural networks because they put, so I will show you ponderation. Hop. So you see that they put 60% on the red model, which is a better legacy model, 20% of the oldest model, and 20% even if this model is better than this. And here you see the number of retraining for the oldest models, so 25 for 3 page. So you can do the estimate. And if I select the Y model, which is the container for the deep learning model, and I will conclude with that. So, every in this year, only 2. So we can also understand why they don't put 100%. That's why we have to do progressively to upgrade the knowledge they wanted to use to learn. And in fact, some of the team are know more things on part of AI than me. It's incredible. This is an exponential curve. Incredible. I'm not a specialist of everything, but this is an exponential curve. Yeah. Thanks very much. Okay. Oh.